But how does ISQ and RFA actually work? How does it work in the technology that we use with our patients? So the way it works today is a little bit different. We are still measuring resonance frequency. But what the technology does is it works a little bit like sonar in a submarine. So it sends out frequencies, but it sends out a series of frequencies and then listens for the echo. And it hears the echo when there is a resonance. That's how it does it. The reason it does it is that this is evolved into a digital technique, which can be done much more quickly. It can be done much more quickly and much more efficiently. And that's with the evolution of technology. So the first real generation of commercial instrumentation was this beautifully elegant machined instrument, again it was designed by Anders Besson, but the electronics were certainly designed by Tim Orr. And what a wonderful piece of antiquaria to have, but it works. And the nice thing was it not only gave the ISQ, but it also gave a profile and a graph as well, which was very useful. And we saw some evolution and technologies of the transducers as we described, and this one is certainly more elegant. It had various little techniques on it, but it could be made relatively easily, and it worked quite nicely. But it highlighted an issue, not a problem, but an issue. So this beam vibrated primarily in its long axis, and that's where it was measuring stiffness. But actually in the patient's mouth, the bone implant stability isn't always the same all the way around an implant. In a edentulous site where the osteotomy is cut for the first time, it may be quite symmetrical. But when we start placing implants in extraction sites, it is anything but symmetrical. And when implants are near to the sinus, then also it's not symmetrical. But we would like to know that. We don't just want to know the best value. We would like to know the worst value, and we like to know how those values change. And this is an important parameter. So we'll have a little bit more of a look. We don't really want to know the average ISQ. And if we map ISQ or resonance frequency around a site, we can see how different it is. And this makes perfect sense. So what can we do? Well, and this is still a technique which is a little bit misunderstood, is we can actually move around, and we needed to make a change to the transducer in order to be able to do that, so that we can find the different stiffnesses. In technical and engineering terms, you will see two primary stiffnesses. You'll see the highest and the lowest. So when a flagpole blows in the wind, it's actually blowing in two directions. It's blowing in one direction, which is the principal, and then it's blowing perpendicular to that as well. And that's what it's important to do. So it's important to measure that stiffness in all directions, and the highest and the lowest. And in order to be able to do that, and in order to be able to evolve the design, the smart peg was designed. And the smart peg is the transducer, but instead of using piezo crystals and wires, it used a little magnet in the top. So it was completely isolated electrically. And the coils, the sensing and transmitter receiver element, were actually in the hand of a probe. And we can see here with the Ostel Mentor how this worked. And it was very nice. This was just simply a question now of holding a probe in close proximity to this smart peg. And you can see here, you can see the asymmetry, and certainly here too. So it is now possible, and it is important to record not just one value, but move the transducer around and record two values, the first mode and indeed the second mode. It may be that you get two numbers that are the same. If you do, it means it's axisymmetric. It's the same all the way around. If it's not, record them both and monitor the changes of both. So that is important. So we have a range of publications, and we'll talk more about that in a moment. The technology further evolved into Ostel IDX, which not only had the ability to make a measurement, but also to record data and Wi-Fi upload it to PC-compatible software. We move back to my vision some 20 years before of thinking about the traffic lights. And could we have a traffic light which was a red warning, amber warning, or a green warning? And who knows, maybe that's the case. And maybe that was part of the vision in terms of the further evolution of Austell into the Austell beacon. So Austell beacon, the beacon is bright and the beacon's Austell.